Center for Philosophy of Science this year. My research focuses mostly on the philosophy of physics. I have some general interest in more general issues in philosophy of science as well, but predominantly philosophy of physics. I study mostly the philosophy of quantum field theory, particle physics, and cosmology, and the sort of boundaries and relationships between those subjects. It's quite fitting that I'm here, given that this is kind of a history and philosophy of science department. I take a very history and philosophy of science sort of lens on understanding scientific theories and theory development. I think of the disciplines that I study as pursuing productive lines of inquiry over time, and looking at how theories are built, how they're confirmed, how we move beyond them, and strategies and methods for learning more about the world as time goes on. One strand of the work that I'm doing while I'm here is a little bit more history focused. I'm looking at the history of the development of particle physics. My dissertation work focused on this, the early stages of building the standard model of particle physics up until its rough completion in the early 1970s. The current work I'm doing here extends on that, looking through the mid to late 1970s, understanding how applications of particle physics to the early universe came to be, and how they're justified as physicists gain more and more hold on these subjects. So this is kind of at the boundary of quantum field theory and of cosmology. I see this work as being both historically and philosophically fruitful. There's a known or sort of folk understanding of the current state of fundamental physics, that there's this incompatibility between our best theories of gravity and our best theories of matter, and to resolve that we somehow need a theory that combines the two, something like a theory of quantum gravity. Well, studying particle physics as applied to the early universe is not going to get us to a theory of quantum gravity. I see it as providing insights into how we can consistently model areas where both gravity and particle physics are relevant, even though those two are incompatible in some theoretical sense. Thinking about these issues will hopefully help to shed some light on how maybe ways of rethinking the merging of gravity and particle physics, as well as help to understand how to think about applying theories to systems where you need a sort of patchwork of different theories over time. Second strand of what I'm doing while I'm here looks at these more general issues in philosophy of science using physics examples. So I'm interested, like I said before, in the process of theory construction. I think of this as a process that happens over time, where we use mathematical method tools, experimental results, new experimental techniques, phenomenological modeling, to kind of arrive at a consensus framework for understanding this domain of physics, and a set of sort of agreed upon unifying dynamical models that describe how the sort of fundamental interactions and how they work. So the current state we're in now, that's a little less historical, is we already have pretty set up and agreed upon theories, general relativity for gravity and the standard model of particle physics for particle physics. And so we have these mature theories, and we're looking for ways to go beyond those. It becomes really hard to do that because the energy scales, given what we currently know, the energy scales that we think that effects that go beyond what we know will actually become observable is well beyond anything we're capable of doing on Earth now, and probably will be capable of doing on Earth for several generations if we want to just use the standard methods of smashing things together and see what comes out. So physicists have had to get creative in how they get around this problem. One of the things I'm looking at is understanding the methodologies that are used in getting around this problem and making more terrestrially accessible evidence relevant for the search for a theory of quantum gravity, or for understanding how our current theories could go wrong.